Welcome to AI Paper Podcast, where we break down some of the most interesting research hitting the AI scene. Today, we're diving into a really compelling paper mapping out, well, what feels like the next big step for AI agents: self-evolving AI agents. Think about AI systems that don't just do things, but actually, learn and adapt and improve themselves continuously over their whole lifespan.
Exactly. That's the core idea. The paper argues, pretty convincingly, I think, that we're moving past these static, fixed LLM-based agents. The new direction is towards what they call self-evolving AI agents, systems designed for continuous autonomous self-improvement, and they frame this with three laws. First, endure, which is all about safety. Agents have to stay safe and stable while changing. Second, excel, meaning they need to keep up or improve their performance, as long as it doesn't compromise safety. And third, evolve. They need to autonomously optimize themselves based on what's happening around them, new tasks, changing environments. It marks this broader shift. We started with model offline pre-training, MOP, then model online adaptation, MOA, then coordinating agents with multi-agent orchestration, MAO, and now the target is multi-agent self-evolving systems, or MA. That's the focus today, how we get there, how it works, and the challenges too.
Okay, let's definitely unpack that vision, AI that genuinely evolves itself. It's quite a leap from just training a big model once, isn't it? It's a whole journey we're mapping out here. So maybe let's ground this first. Where are we right now? LLMs, large language models, they've gotten incredibly good at reasoning, planning, understanding language.
Oh, absolutely. The progress has been phenomenal.
Yeah.
And that's led directly to these LLM-based agents, right? Systems that use an LLM as their core, their brain, essentially, to act autonomously.
But an agent is more than just the LLM itself.
Right. It's a whole system. You've got the foundation model, the LLM, doing the heavy lifting on interpretation and planning. But then you need these supporting modules, things like perception, how the agent actually gets info from its environment, text, images, code, whatever. Then the planning module, which is super important. It's how the agent breaks down goals. We've seen different approaches here. Chain of thought for step-by-step reasoning.
Like thinking it through line by line.
Exactly. Or react, which is more iterative, kind of acting and reasoning in a loop. And even things like tree of thought or graph of thought, exploring multiple possibilities. Then there's memory. You need short-term memory for the current task context and long-term memory to build up knowledge over time, often using RAG, retrieval augmented generation, to pull in external facts. And finally, tools. Agents need ways to, interact with the outside world, use a search engine, run code, control a browser. That extends their capabilities massively.
It's quite a setup, sophisticated stuff. But here's where it gets really interesting and where this paper picks up. Most agents, once you build and deploy them, they're kind of stuck, right? They're static.
That's the bottleneck. The real world isn't static at all.
Not even close.
So if you have, say, a customer service agent and the company launches new products, or a scientific assistant agent and a better algorithm comes out, well, tough luck for the agent. Someone, a human developer, has to go back in, manually reconfigure the prompts, maybe update the tools, potentially even retrain parts of the model. It's slow, it's expensive.
And it just doesn't scale if you want these agents to be truly useful long term.
Precisely. And that's the core motivation for this idea of self-evolving AI agents.
Okay, so let's define that clearly then. Self-evolving AI agents are what? Autonomous systems.
Yeah, autonomous systems that can continuously, systematically optimize their own internal parts. They do this by interacting with their environment. The aim is adapting to changes, new tasks, different contexts, maybe limited resources, but, and this is key, always keeping safety paramount and trying to boost performance.
Which brings us neatly to those three laws you mentioned. They sound fundamental.
They really are positioned that way in the paper, drawing that explicit parallel to Asimov's laws, and they're hierarchical. Law number one, endure. Safety adaptation. The agent must stay safe and stable during any self-modification. Non-negotiable.
Safety first, makes sense.
Absolutely. Law number two, excel. Performance preservation. But subject to the first law. It has to maintain, or ideally, improve its performance on tasks.
So get better, but not if it makes things unsafe.
Exactly. And law number three, evolve. Autonomous evolution. Subject to the first two laws. The agent should autonomously optimize its components, prompts, memory, tools, whatever, when things change.
So it's a constrained optimization. Evolve, yes, but only within the bounds of safety and performance.
Precisely. That hierarchy is critical. It provides the necessary guardrails.
Okay, that framework is clear. And you mentioned this is part of a wider paradigm shift. Can you walk us through those stages again? MOP, MOA?
Sure. It helps to see the progression. We started with MOP, Model Offline Pre-training. This is like the classic approach. Train a massive model on a huge data set, freeze it, deploy it. Think early GPT models, BERT, static entities.
Train once, use forever.
Pretty much. Then came MOA, Model Online Adaptation. This was a big step. Models could actually learn after deployment. Techniques like supervised fine-tuning using things like LoRa or reinforcement learning from human feedback, RLHF.
Like the Instruct GPT or early Chat GPT work, adapting based on interaction.
Exactly. Making the models more aligned or specialized post-training. Then we got to MAO, multi-agent orchestration. The focus shifted. Instead of just one super smart agent, let's coordinate multiple agents. They communicate, maybe debate, collaborate on complex tasks. Think frameworks like Camel or Autogen. But crucially, the underlying agents themselves usually weren't changing their core parameters much. It was about coordinating static agents.
Okay, coordinating the team rather than improving the players individually.
Yeah, that's a good analogy.
Yeah.
And that leads us to the final stage, the target here. MAS, multi-agent self-evolving systems. This is the vision of a lifelong self-improvement loop. Agents continuously refining everything, their prompts, how they manage memory, their strategies for using tools, even how they collaborate with each other, all driven by feedback.
Wow, okay, so that's the destination. MASA, how does that actually work conceptually? You mentioned an optimization process.
Yeah, the paper frames it as an iterative optimization cycle with 4 main parts. First, you have the system inputs, the task description, the data, the context the agent needs. Second, the agent systems themselves could be one agent, could be many. Third, the environment. This is critical. It's where the agent acts and gets feedback. A compiler saying code passed or failed. A database confirming a fact.
The reality check.
Exactly. And fourth, the optimizers. These are the engines driving the evolution. They figure out what to change in the agent, the search space, like which prompts or tool parameters and how to change it, the optimization algorithm used based on that environmental feedback.
Got it. So inputs agents, environment feedback, optimizer, tweaks the agents, repeat.
That's the loop, yeah. Constantly trying to get better according to those 3 laws.
Okay, this is making sense. So how does an agent actually optimize itself? Let's maybe start with just a single agent first. What can it change?
Right, drilling down into the specifics. The paper identifies 4 main areas for single agent optimization. First up is LLM Behavior Optimization. This is about making the core LLM itself better at reasoning and planning for the task at hand. You could do this through training-based methods, maybe fine-tuning the LLM using supervised examples of good reasoning, like the Torah approach, or using reinforcement learning where the agent gets rewards for successful reasoning steps, like self-rewarding models.
So actually changing the LLM's weights.
Correct. Or you can do it at test time during inference without retraining. This could be feedback-based using an external checker, like a compiler for code or a theorem prover for math, to verify the output and maybe guide retries.
Like getting instant feedback.
Yeah. Or it could be search-based, where the agent explores multiple lines of reasoning before picking the best one. Think chain of thought self-consistency, or more complex methods like tree of thoughts or graph of thoughts.
Okay, so improving the core brain. What's next? The instructions we give it.
Exactly. Prompt optimization. How do you find the best way to ask the LLM to do something? This is a huge area. You have edit-based methods that start with a human-written prompt and iteratively tweak it, inserting words, deleting phrases. Think grips or tempora. Then generative approaches where LLMs actually write brand new prompts from scratch based on what works well, like APE or OPRO.
The LLM optimizing its own instructions. Meta.
Very meta. There are also text gradient-based methods using natural language feedback, like this response needs to be more concise, as a signal to update the prompt. Protege is an example. And even evolutionary algorithms, treating prompts like populations that mutate and cross over to find better versions. EvoPrompt, prompt breeder.
Fascinating. Okay, so better reasoning, better prompts. What about memory? Agents need to remember stuff.
Crucial. That's memory optimization. How does the agent better store, retrieve, and use information? For short-term memory, it's often about managing that limited context window LLMs have. Maybe automatically summarizing conversations or using reflection techniques like reflection to extract key insights from past actions to guide future ones.
Making the most of what it can see right now.
Yeah. And for long-term memory, it's about building persistent, scalable knowledge stores. Things like specialized memory architectures, AMEM, MEM0, that go beyond simple vector databases, allowing structured storage and retrieval over long periods.
Got it. And the last piece for single agents, tools.
Right. Tool optimization. making the agent better at using external tools, or maybe even figuring out new ways to use them. Again, you can do this via training, fine-tuning the LLM specifically on examples of tool use, like Tool LM or Gorilla, or using RL to reward successful tool interactions.
Teaching it how to use the tools properly.
Or you can optimize at inference time. This might be prompt-based, like automatically refining the tool descriptions given to the LLM so it understands them better. Easy tool. Or it could be reasoning-based, using clever search algorithms to plan sequences of tool calls for complex tasks, like tool chain or tool planner.
Okay, wow. That's a lot of ways a single agent can evolve. It's like every part of its mind is potentially up for optimization. Now, you mentioned Amaze, multi-agent self-evolving. How does this scale up? What happens when you have multiple agents or agents working in very specialized domains?
Yeah, that's the next layer of complexity. With multi-agent optimization, the game changes slightly. It's not just about optimizing individual agents, but optimizing the entire system, how they interact, who talks to whom, what roles they play. So you still have prompt optimization, but now it's about refining the instructions for each agent within the team, maybe using frameworks like DSPy to manage that. But you also get topology optimization. This means optimizing the actual structure of communication. Who should agent A talk to? Is agent B's input really necessary? Techniques like agent prune try to remove redundant communication pathways.
Streamlining the team's workflow automatically.
Exactly. And there's unified optimization, trying to optimize multiple things at once, like the prompts and the communication structure simultaneously. EvoAgent and EvoFlow are examples exploring this. And then there's even LLM Backbone Optimization, where you might fine-tune the underlying LLM specifically to be better collaborators, perhaps more efficient communicators, or better at understanding shared goals.
It's like tuning not just the players, but the team's formation and playbook too.
That's a great way to put it. And then you have domain-specific optimization, which is crucial for real-world applications. General LLMs are amazing, but they might lack deep expertise or the specific reasoning patterns needed in, say, biomedicine. So we see agents optimized for medical diagnoses, using dialogue strategies and integrating external knowledge bases, like Methodologies, or for molecular discovery, where they need precise chemical reasoning and integration with tools like RDKit, KTS ChemAgent.
Tailoring the evolution for specific expert tasks.
Precisely. Same in programming. Agents optimized for code debugging, using execution traces to pinpoint errors, self-debugging fix agent, or for code refinement. And in financial and legal research, multi-agent systems for trading strategies, trading GPT, or agents designed for legal reasoning, understanding rules, analyzing evidence, maybe even simulating court procedures. LawLuo, Agent Court.
This is incredibly powerful stuff. The potential seems enormous, but it also sounds like it could get complex, maybe even unpredictable, very quickly. This brings us back to safety, to that first law, endure. How do we evaluate these constantly changing systems? How do we ensure they stay safe?
That is the critical question, and the paper rightly emphasizes it. Safety isn't an afterthought. It has to be baked into the entire evolutionary process. Every change needs scrutiny. On the evaluation methodologies front, we're seeing progress beyond simple accuracy scores. We have sophisticated benchmarks now, simulating complex web tasks, Web Arena, testing multi-agent collaboration, multi-agent bench, GUI interaction, Android world, and those domain-specific ones like SWE bench for coding or agent cleaning for medical AI.
Benchmarks that try to reflect real-world complexity.
Exactly. And methods are changing too. There's LLM as a judge, using powerful LLMs to assess the quality or helpfulness of other AI outputs. It's useful, but sensitive to how you prompt the judge LLM. An even more interesting direction is agent as a judge. Here, you use a whole separate agent system with its own reasoning and tool use to evaluate the entire process or trajectory of another agent, not just the final answer. This gets closer to how a human expert might assess the work.
So the evaluation itself is becoming more agentic, more sophisticated. How does this help with safety specifically?
Well, for safety, alignment, and robustness, the link to the Endure law is direct. We need ways to continuously monitor agents as they evolve. Researchers are developing risk-focused benchmarks designed to tempt agents into unsafe behavior, like agent harm testing responses to malicious requests. And behavioral probes, like the Machiavelli benchmark, look for emergent, unethical, or manipulative strategies that might arise during optimization.
Trying to catch problems before they happen or as they emerge.
Right. But a key challenge highlighted is that most evaluation today is snapshot-based. We test the agent now. From AC, we need dynamic, longitudinal evaluation tracking safety and alignment over the agent's entire evolutionary lifespan. That's a big gap we need to fill.
It definitely sounds like a major challenge. Okay, so looking ahead, what are the biggest hurdles still standing in the way of realizing this vision of self-evolving agents? And what are the most exciting research directions?
The paper lays out several open challenges, and they map nicely back to the 3 laws. Under endure safety adaptation, the big ones are ensuring optimization doesn't accidentally sacrifice safety for performance metrics. How do we build evolution-aware auditing? How do we handle noisy reward signals that might destabilize the agent? Regulation is a huge question mark, too.
Right, how do you regulate something that's constantly changing itself?
Exactly. Then, under Excel performance preservation, evaluating performance in cutting-edge science or specialized domains where there's no easy right answer is tough. Balancing the sheer computational cost of optimizing large multi-agent systems with getting effective results is another hurdle. And making sure optimized prompts or agent structures aren't brittle, that they actually transfer if you swap out the underlying LLM.
That transferability issue seems key for practicality.
It really is. And finally, under Evolve Autonomous Optimization, most work is still text-based. We need agents that can handle multimodal input, vision, audio, and reason spatially for real-world robotics or interaction. And tool use, moving beyond just using predefined tools to agents that can discover, adapt, and maybe even create their own tools. That's a major frontier.
So, quite a list of challenges, but presumably researchers are already working on these. What are the promising paths forward?
Definitely. The paper points to several key areas. Developing more sophisticated simulated environments is crucial for safely testing and training fully autonomous MAE systems. Really pushing the boundaries on tool use and creation of adaptive selection, composition, maybe even co-evolving tools alongside the agent. Building those real-world evaluation systems we talked about, ones that capture complexity and allow for that longitudinal safety and performance tracking. Designing MAS optimization algorithms that explicitly consider the trade-off between performance and computational resources, making them efficient enough to actually run. And continuing to tailor evolution methods for specific domains, integrating deep expert knowledge, and handling things like regulatory compliance in fields like medicine or finance.
It really feels like we're watching the blueprint for a new kind of AI being drawn up, moving from static tools to systems that are, in a sense, alive, learning, adapting, lasting. The focus isn't just on making them smart, but on enabling them to become smarter, better versions of themselves, hopefully safely.
That's a perfect summary. These self-evolving agents, or the pursuit of them, really bridge the gap between the powerful but often static foundation models we have now and the kind of continuous adaptability we expect from intelligent systems operating in the real world over long periods. And those 3 laws, endure, excel, evolve, they're not just a clever framing. They represent crucial design principles, practical guardrails needed to steer this powerful evolution in a beneficial direction. Safety, performance, adaptability in that order.
It definitely leaves you thinking, if AI agents truly gain the ability to autonomously evolve their own designs, their own ways of working, how does that change our role? What does it mean to develop and deploy AI when the systems themselves take over part of that development process? Definitely something to chew on. Thanks for walking us through that fascinating stuff.
My pleasure. It's a rapidly evolving field, that's for sure.